So today we are going to discuss the rest part of the uh, module 4, which is last class we have discussed about the patterns. So today we will discuss about the field pattern and power pattern. So sine wave, 1 minute. Okay. So last class we have discussed about the power pattern, okay, and radiation intensity. How to calculate the radiation intensity for the various pattern, whether it is a cosine, whether it is a sine, or whether it is a depend upon the variation of the fields. Now today we are going to discuss about the field pattern. The field pattern with respect to electric field and with respect to magnetic field. If any of the field is known, the perpendicular direction will identify as the rest of the component. Suppose our total wave is propagating along z-axis, electric field may propagate along x-axis. If it is along x-axis, then magnetic field will propagate along y-axis. So both are transverse with each other, both are perpendicular to each other. Now if one of the field pattern is known, the other field pattern is easily to identify, because when these waves are transmitted into a particular air medium or a free space medium, and we have a certain relation, that intrinsic impedance, which form a ratio between electric field and magnetic field. If you know the electric field, you can easily determine the magnetic field with the help of a relation that E by H is equals to eta, and this eta for air medium, it is 120 pi. So if electric field pattern is known, then magnetic field pattern can easily be identified. By simply dividing E divided by 120 pi, you will get your magnetic field pattern. So how to identify this pattern? Now last class we have discussed about the point source. So if the point source is identified at a certain point, and we have seen if the measuring point is at a fixed point Q, and what is the distance measured with respect to near field, measured with respect to far field, measured with respect to the reactive near field, Fresnel zone and Fraunhofer zone. Basically we are measuring the effects at a far field position, that is called Fraunhofer positions, okay, and depend upon that relation we have identified certain patterns, certain relations, relative values also we have identified. Now in today's class we are going to identify with respect to the component, field component. So field component, if I will say, that means what are the field components will available with respect to electric field and with respect to magnetic field. If any of these fields are known, the other fields can be easily determined with the help of the Maxwell's equations. Okay, so let us proceed how to identify these particular fields. Now here I have drawn one three-dimensional view of a sphere. Okay, now why I have drawn this particular sphere? The question will arise. The answer is, whenever we are considering a point source, it will spread throughout the space, okay, throughout the space in a spherical manner, okay, and wherever this radius, if you take, it will take as a constant radius, okay, and throughout the sphere there are variations will depends upon radius of a sphere, azimuthal angle, that is phi, and the angle which is followed by a radius, that is angle theta. So these are the three components which comes into picture in order to identify the field pattern. Okay. Now here you can see that there is a sphere, and I have kept my point source at point O. Here at point O, the point source is available, and when the point source is available, the field's component will move out. So if the field components are moving out, that is called radial components are available. Okay, and once these radial components are there, and if you rotate this sphere in the anti-clockwise or clockwise direction, other component will come into picture. If you rotate it, your phi component will come, and if you vary this radius from z component to plus z to minus z, then angle theta will come into picture. And the variations, as we know that radius will have a fixed position, fixed distance, theta will lies between 0 to 180 degree, and the phi will lies between 0 to 2 pi degree. So depend upon these two consideration, we can proceed further. So here I have written power flow from a point source. Okay, power flow from a point source must be a radial component. That means when I am considering point O as a point source, the radial component which is coming out from this particular point and measured at a certain point P. So that component is called as a radial component. So always remember that when a point source is available in a certain space, it will spread the fields in a radial outward. And always remember that if the fields are moving radially outward, that means we are considering with respect to electric fields. Okay. If it is circular in nature, then you can consider for the magnetic field. So if you identify electric field first, it is easy to determine the magnetic field patterns. So once this electric field is known, then you can determine the magnetic field with the help of this sort of relation. Okay. So first relation is the power flow from the point source has only the radial component. Yes, it is a radial component, and this radial component is a scalar quantity. It is a constant value. Done. So this is the first point. At far field, E and H field are perpendicular to each other. Yes. At far field means at a Fraunhofer zone, when r is greater than 2d square by lambda. When r distance is greater than 2d square by lambda. This is called Fraunhofer zone, or it is called as a far field zone. At the far field zone only we are measuring the field patterns, electric field and magnetic field, and at that point the electric field and magnetic fields are perpendicular to each other. Okay. So if one of the component is known, other component can be easily identified. Next, how to analyze this particular point? We have two steps. First, we have to identify the power flow. So now how to identify the power flow? The power flow is identified with the help of Poynting vector. Remember that. So Poynting vector means it is a cross product of E cross H. If any of the component is known, other component can be easily identified. So here the Poynting vector source at a point P is a radial component. This point P is a radial component that I have written, it is called S suffix R. So this S suffix R is a Poynting vector scalar component, Poynting vector source point, which is radially outward. 1 minute. Radially outward. So and E theta and E phi are transverse with each other. Now if you consider a point P over in this sphere, let us consider at point P. So at this point we have the positional vectors, three positional vectors we have. One with respect to r, one with respect to theta, and one with respect to phi. So here in this point I can say it is r, theta and phi. So r, theta, phi is the point at the point P, and that positional vectors can be easily identified. So along r direction S suffix r, along theta direction it is E theta, along phi direction it is E phi. So these are the three positional components available at point P. Okay, and this SR is identified with respect to the Poynting vector. So here it is Poynting vector source point, which is coming out as a radial in nature, and E theta, E phi is a transverse in nature, perpendicular to each other. So you can see E theta and E phi both are perpendicular to each other with respect to the radial component of Poynting vector. Then at far field, because whatever we are measuring at the far field. So point source is available at origin and we are measuring the effect at a far field. So far field means this R must be greater than 2d square by lambda. D is the dimension of the antenna, lambda is the wavelength at which the wave is propagating, and R is the far field distance. Okay. So for far field, the two things we have to consider. One is Poynting vector radial component, so that is SR, and electric field component along theta and phi. So electric field component along theta and phi. So these are the three basic considerations to measure the patterns. One, Poynting, because the power depends upon a vector called Poynting vector through which electric field and magnetic fields are analyzed. Second, the rotations depend upon the nature of a object. Suppose here I have considered with respect to sphere. So in sphere other two dimensions are available, that is theta and phi, and both are perpendicular to each other. So if I am identifying the fields as a radially outward, that means it is considered as a electric fields. So electric field will have three components, one along r direction, one along theta direction, one along phi direction. So along r direction we have represented the Poynting vector, and along theta and phi we have represented the electric field transverse in nature. Now once this is done, then we have to form a relation. Then what will be the relation with respect to SR, with respect to E, with respect to the field component sum. And now as we know that the power, okay, the power flow through a particular wave, or when we are dissipating a power in a particular direction in a form of wave, that means the power relation will come into picture as either we can represent power as half E naught square by eta, or half eta h square. Like that we can represent either in terms of electric field or in terms of magnetic field. The same analogy we are going to use here, because the power identified with respect to the radial component of Poynting vector. So SR is equals to half E square divided by Z naught. Now what is Z naught? Z naught is nothing but the intrinsic impedance. Now here we have considered only the magnitude of electric field. Now here electric field is having two other components, one is theta and one is phi. So here E is nothing but E is equals to root over of E theta square plus E phi square. And what is Z naught? Z naught is called as our intrinsic impedance. So these are the two considerations through which we have derived the relationship between the radial component of Poynting vector, or Poynting vector radial component you can say, with respect to E theta and E phi. So E theta square plus E phi square root over, we will get the magnitude of E, and SR is the Poynting vector source point radially outward, and it is measured with respect to electric field. Now this electric field, if you know, then it is easy to determine the magnetic field component, okay, because as we know that this power can also be written in terms of half h naught square into eta, like this. E is equals to eta naught, we can write eta square, eta will be cancelled out, into h square it will be, so it is half h square into eta also we can write. Similarly it is half E naught square into eta we can write. So if any of the component is known, other component can be easily determined, just perpendicular to each other, okay. So this is the relationship between the Poynting vector, which is radially coming out from that point, source point, with respect to the transverse electric field E theta and E phi. So far field may be elliptical, linearly polarized in nature. So at a far field, the fields are in a form of elliptical, okay, in a form of elliptical with having a minor axis and major axis with a certain beam width, okay, that we have seen in the last class, and it can be a linear and it is a polarized. Polarized means at a certain direction, okay. So these are the fundamental terms which come into picture when we are discussing about the field patterns. Now once this fields pattern is known, next we can proceed for the power pattern. So power pattern, how we can determine? Power pattern will be identified with respect to the field pattern, but with respect to the relative in nature, relativity, okay. So here I have discussed about the relative field pattern. So once this relative field pattern is known, it is very easy to determine the power pattern. We will see all those relations step by step. So relative field pattern means it is relative to itself with respect to the maximum value. For example, as we have discussed last class, this is a radiation pattern, okay, and this is the SR and this is SRM, okay. SR is the radial component you can consider for the Poynting vector, and SRM is the maximum radial component. So relative value, if I will say, it is SR divided by SRM. So this is the relative value. This is called as a relative pattern. If you divide SR by SRM, the maximum value here it will be 1, and here it will be SR divided by SRM. Like that we can analyze. That is called relative pattern. And once this relative pattern is known, power pattern can be easily determined by taking the square of that relative value, okay. So how it is? Let's see. So it is relative to its reference direction. Yes, it is relative to its reference direction. Then relative pattern with respect to E theta, because here the E theta and E phi are the two transverse electric fields, and one is radial component, that is Poynting vector. So if there are two transverse components are there, we can easily determine the relative value. So for relative pattern of E theta, can be identified as E theta divided by E theta m. E theta m is the maximum value of E theta. So this is E theta divided by E theta m. So this is called as a relative pattern for E theta. Similarly, relative pattern for E phi, that we can determine as relative pattern for E phi, that is E phi divided by E phi m. So what is E phi m? E phi m is the maximum value of E phi. For example, if I will write E phi is equals to cos phi, okay, is equals to 2 cos phi. Then now what is the maximum value of this? The maximum value will be obtained as 2 when phi is equals to 0 degree. So this is the maximum. If you divide this E theta by E theta m, you will get your relative field pattern, and that relative field pattern is it in the terms of cos phi. Simple, okay. So this thing we have to keep in mind. Now this E theta is the maximum value of E theta and E phi m is the maximum value of E phi. But as we have a relation that electric field will change, the electric field value will change with respect to the change in position, because as we have seen our derivation that E is equals to Q divided by 4 pi epsilon naught R square, like that. So E is inversely proportional to R square. So if E is inversely proportional to R square, means the magnitude of the electric field will vary with respect to the change of position. So if I will change the position, my field pattern is also get changed. So how it will change? Let's see. So there are two transverse electric field. One is E theta and one is E phi. So these are the two fields. Okay. Now E theta is inversely proportional to 1 by R and a function of theta and phi. Okay. So F1 is a function. It is a dependent function, depends upon theta and phi. But it is inversely proportional to R. So E theta is inversely proportional to R. Similarly, E phi is also inversely proportional to R, where F2 is another function, depends upon theta and phi. Because here you can see, if theta and phi are transverse with each other, that means these are interrelated with each other, and theta depends upon phi and theta also. Similarly, phi depends upon theta and phi also. So these are the two field patterns which are having a certain distinct function, and these field patterns will change with respect to the positions. If you change the distance, your field patterns are also going to change. Okay. Then what is F1 and F2? F1 and F2 are the two different functions. Dependent functions on theta and phi. Now, next one is called as our power pattern. So how to determine this power pattern? Now, as here we have seen that SR we have identified. SR means it is, as I have represented SR and SRM. SR is the pointing vector, which is radial component coming out from that point, source. So what we have identified, SR with respect to electric field, it is half E square divided by Z naught. What is E? E is root over of E theta square plus E phi square. And what is Z naught? Z naught is our characteristics impedance. So this is our SR. Now suppose, what is the maximum value of SR? If I know what is the maximum value and I will divide with respect to SR, then I will get the relative pattern. Okay, relative power pattern. So here SRM is the maximum value. SRM, when it will maximum? When the electric field identified as a maximum, when the electric field achieves the maximum value. So EM square divided by 2 Z naught. For example, E is equals to, after this solution, E is equals to 2 cos theta we have identified. Let us consider the same example, 2 cos theta. So what is our EM? EM is 2 at theta is equals to 0 degree. So if you divide E by EM, you will get cos theta. So that is one relative field pattern. Similarly, SRM is equals to EM square divided by 2 Z naught, where EM is the maximum value of electric field. So maximum value of electric field is how much? 2. So you have to substitute 2 here, square it divided by 2 Z naught, you will get SRM. Now, power pattern, how I will identify? Power pattern is identified by taking the ratio of SR divided by SRM. So SR is this Okay, and SRM is how much? SRM is the maximum value. If you divide these two, you will get your power pattern. This is called power pattern. Okay, so power pattern. Now this power pattern depends upon the intensity because it is directly proportional. So I have written U by UM. So what is U? U is the radiation intensity. And what is UM? UM is the maximum radiation intensity in a particular direction. And what is the relationship between intensity and field? It is just a square component. So here we can directly write E divided by EM whole square. So what is E? E is 2 cos theta. What is EM? EM is 2. If you divide this, we will get cos square theta. So my radiation pattern will have the cos square theta terms. So this is called my radiation pattern, power pattern. Okay, radiation pattern depends upon intensity. Okay, similarly field pattern depends upon electric field intensity and the Poynting vector. Now if I want to discuss about the power pattern, you need to square that intensity. You need to form a relation between intensity with respect to the maximum intensity in that direction. And if you take a square of electric field with respect to the maximum electric field, it is a power pattern we can identify. It is a simple example I have wrote. If E is equals to 2 cos theta, what is the maximum value of E? Maximum value of E is 2. At which particular degree? At theta is equals to 0. Now if you substitute this component here, okay, E divided by EM, so 2 will be cancelled out, you will get cos theta and cos theta whole square. So that is power pattern. So if it is only cos theta, EM by E by EM, then it is called as a field pattern, relative field pattern. But if you square it, it will get as a power pattern. So this is the simple steps to identify what is the difference between field pattern and what is the difference between power pattern. Okay, if it is field pattern, it is only cos theta. Okay, E by EM. But if it is a power pattern, you need to square it. Okay, so here it is EM by E by EM. If you divide these two, you will get cos theta. Square it, that is called as a cos square theta. So cos square theta is the power pattern with respect to the given electric field status. Okay, so these are the basic steps through which we can proceed further discuss about the certain cases. Okay. Okay. So these are the three basic cases through which we can analyze the field pattern as well as power pattern. Okay. So field pattern already we have discussed in the previous class, and today we are going to discuss about the power pattern with respect to the field. How we are going to identify with the help of the relation what we have discussed now. Okay. So step by step for case 1 we will see. So case 1, the source with cosine field. Okay. If the source is a cosine field, then what will be our radiation pattern? As I have discussed in the previous, if your E is equals to 2 cos theta. Okay. What is the E maximum value? 2. At which degree? Theta is equals to 0 degree. So when you are identifying the relative field pattern, your E divided by EM reflect as a cos theta. So that is called as a cos theta. If your source is a cos theta, that means we can follow and find out the radiation pattern. Let's see how to determine. So source with a cosine field term. You can see this cosine field term. It is look like this. Already we have discussed the cosine signal. Okay. And for the far field, only we will have the E phi component and E theta will 0 because it is a cosine signal. You can see this is only the phi term is available and theta term is not available. So this phi depend upon the phi component and E theta is 0 because these are the two transverse field as we have discussed now. So those two are perpendicular to each other. Now if it is only the point source, that means either sine or cosine. But if it is a short dipole or a loop antenna, that means it is a combination of a sine and cosine will be available. That we will see now. Okay. So the relative field pattern here we can represent as E phi divided by E phi m is equals to cos phi. Then is equals to cos phi. This is called as our cos pattern, cosine field pattern. Now I have to identify the power pattern. So what is the relationship? The power pattern is P is equals to SR divided by SRM, which is equals to U divided by UM, which is equals to E divided by EM whole square. So E divided by EM is how much? Cos phi. We need to square it. So E phi divided by E phi M whole square, we will get the power pattern as cos square phi. So field pattern is cos phi, but power pattern is a square of the field pattern. Then, so if you square it, it will become narrow component because maximum value will be identified. Suppose maximum value is 0.5. If you square it, you will get 0.25. That means it is lesser with respect to the field pattern. So it will narrow beam will be identified. So this is the narrow beam is identified. Okay. So this narrow beam is called as a power pattern, and this one is called as a field pattern. So this is field pattern and this is called as a power pattern. Done. Similarly, if the source with sine term, done. If the source is with sine term, so what will be the relative fields? So sine term means your phi component will be 0 and theta component will exist. So sine will look like this. So sine pattern is this one. So here phi component is 0 but theta component will exist, and the theta depends upon sine phi. So the relative pattern or relative field pattern, you can say E theta divided by E theta m is equals to sine phi. So that is called as a field pattern. But when you are going to calculate for the power pattern, you need to square it. So as I have told, the power pattern is equals to SR divided by SRM, which is equals to U divided by UM, which is equals to E divided by EM whole square. So what is E theta divided by E theta m? It is sine phi. Square it. You will get sine square phi. Similarly, same thing I will tell. If the sine theta term is 0.5, what will be sine square? If sine phi is 0.5, what will be the sine square phi? Sine square phi means it is 0.5 whole square 0.5. It is narrower with respect to the field pattern. So here you can see this is called my field pattern and this is called my power pattern. The amplitude will reduce, the beam will be narrow. Here the beam is wider, here the beam will be narrow. Okay, so this is called as our sine field. But when we discuss with respect to the loop antenna or with respect to the dipole antenna, in which it is a combination of sine and cosine, so we cannot neglect any of the component. Here we have to consider E theta as well as E phi term. Okay, then only the maximum electric field we can identify. So if you consider with respect to theta, E theta as the cosine wave as a cos phi, similarly E phi can be considered as a sine phi. So maximum value will be sine square phi plus cos square phi, that will be 1. So your power pattern will 1 means it is a unit circle we can determine. Let's see how to represent. Okay. So antenna for the far field region, E theta and E phi both are perpendicular to each other. Okay, both are perpendicular to each other and both are existing. Then in these two antenna, in the short dipole and loop antenna, it is not a point source. In point source, we can either consider sine wave, either consider cosine wave. But if it is having certain dimension, if it is having certain length, then the E theta and E phi component will exist. Definitely it will exist. Okay. So for the short dipole and this or for small loop antenna at the far field distance, your magnitude will become equal, because distance increases means electric field intensity deteriorates. So when it is deteriorating, both the field components are inversely proportional to R, and at a far field distance both magnitude will become equal. Okay. So if it is equal, then your maximum value E by EM, so that is nothing but root over of E theta square plus E phi square. In place of E theta substitute sine square phi, in place of E phi substitute cos square phi. So sine square phi plus cos square phi, resultant is 1. So resultant is 1 means this is E by EM. Then what will be my power pattern? This is the field pattern. Okay, this is relative field pattern. And what will be my power pattern? So power pattern is Em divided by Em whole square, that is equals to 1 whole square, that is equals to 1. So that means if it is 1, it is called as unit circle. So this is the power pattern for the short dipole and loop antenna. But if it is a field pattern, this upper circle is our cos wave, okay, and the side circles are called as our sine wave. Done. So my circle will lies, if you join the edges point of these circles, you will get your power pattern. So here I can say this is my E phi and this is my E theta, and this E phi and E theta are perpendicular to each other. So E theta is how much? Sine square phi. What is E phi? It is called as cos square phi. Magnitude is how much? Resultant is 1. So if the E by Em is 1, power pattern will be how much? Power pattern will be 1. So it is a unit circle. So this is the field pattern, this is the power pattern. So like this we have to analyze. So depend upon the various sort of antenna, the field pattern and power pattern will change. If the point source is there, either we can go for cosine or sine. But if there are the elements are there, certain lengths are there, then we cannot neglect any of the component. We have to consider both of the component and we have to identify the power pattern. So like this, these are the three basic cases through which we can understand about field pattern and power pattern. Okay, so this is the special case for the point source if there are more than one number of point sources available. Okay, first we will discuss if the 2 point source are having the same amplitude and same phase. Second case we will see if it is having same amplitude and opposite in phase. These are the two special cases we will see with respect to the array of point source. So here array of 2 isotropic point source we are identifying. 2 point source means, let us consider these are the 2 point source, point 1 and point 2 are separated at a distance d, and the center point is O, so distance is half of d, so d by 2 and d by 2. So if you take a total distance between point 1 and point 2, it is d. Basically this concept comes into picture when we are discussing about the dipoles. One point will act as a positive, one point will act as a negative. So if it is a like that case at a certain distance d, we can easily find out what is the electric field intensity due to the dipole. Similarly, for the identification of that analysis, first we have to analyze, or first we have to understand what are the field components are going to come at a certain point P when we are measuring from two different point source when it is having the same amplitude with the same phase component. Okay, so let us discuss first this one. So with the same amplitude and same phase. Okay, second case we will discuss same amplitude with out of phase. What will be the changes, that we will see. Now as per the figure, there are 2 point source I have considered, point source 1 and point source 2, separated at a distance d, and center point is O. So half of the distance from O to 1 is d by 2, O to 2 it is d by 2. And these are the field components are generated. One field is identified with respect to source 1 and one field is identified with respect to source 2. So source 1, if I will see, the point is identified in downwards and point 2 is identified in upward. So I can consider imaginarily which is moving down, I can consider it is a minus sign, and which is moving upward I can consider as a positive sign. So let us discuss first. So what is dr? So dr is depend upon the distance. Okay, distance at a far field region, that is 2 pi d by lambda. So it is 2 pi d by lambda. So 2 pi by lambda is beta. So beta into d. So this is the total field at a large distance r in the direction of phi, because when we are identifying the point source, it is identified in terms of phi. So E theta terms, either you can consider E theta terms or we can consider phi terms. So here we have considered phi terms. So E is equals to, first due to the point source 1, it is E naught e to the power minus j sigma by 2 and E naught e to the power plus j psi by 2. So this is due to the source 1, this is due to the source 2, because according to the phasor diagram you can see that first one which is moving upward, that is due to the source 2, and which is moving downward, it's called as a source 2, source 1. So it is e to the power j minus j psi, and this is e to the power minus j psi by 2. So depend upon the angle. So this angle, total angle is psi, and if you divide it, you will get is your total value. So that I have represented E naught e to the power minus j psi by 2 plus E naught e to the power plus j psi by 2. Now here E naught is common. Take E naught common and you will represent this whole component in terms of cos. So you have to multiply 2 and you have to divide 2 to this component. So here I have written twice of E naught e to the power j psi by 2 plus e to the power minus j psi by 2 divided by 2, you will get in terms of cos of psi by 2. So it is twice e naught cos psi by 2. Now what is the psi term? Psi is the phase difference between these two sources. Phase difference. So here you can see these are the 2 point source separated at a distance, and if I will take a source, the path difference here you can see it's a d cos phi. So this psi is nothing but dr cos phi. It is a path difference. Remember that. So psi is equals to dr cos phi. So in place of psi you have to substitute dr cos phi. What is dr? Dr is the far field distance, that is beta into d. So it is dr by 2 into cos phi. So this is the total electric field pattern. So 2 E naught is the maximum amplitude. So cos of dr by 2 into cos phi. So when this component will have a maximum value? When this component is 0. So cos of 0 is 1. So for that, this phi term must be 90 degree. Okay. Then only we will get this cos term as maximum, and the electric field will have maximum value 2 E naught. Same. So for consideration, for twice E naught is 1, normalized condition. So if the twice E naught is 1, d is equals to lambda by 2, this dr is lambda by 2, d is equals to lambda by 2, and this dr is pi. If you substitute this, you will get E is equals to cos of pi by 2 and cos phi. So this is the one condition through which we can identify the pattern. So here E is equals to cos of pi by 2 cos phi. That means this is the electric field pattern for 2 point source, array source. Okay, 2 point source positioned at a certain distance d. So this is our field pattern. If anybody asks what is the power pattern, you need to square it. Okay, the square term means cos square of pi by 2 cos phi. That is called as a power pattern. This is called as our field pattern. Next, if the source is located at origin, now in this case the 2 point sources are separated at a distance d, which is midpoint is our origin. Now second case, what happens if this point is shifted to O and this 2 is shifted to another position at say a distance d. So what will happen? So if this 1 is shifted to O, that means there is no phase change, and there is only the phi will come into picture with respect to the source 2. So if the source 1 is located at origin and source 2 is located at a distance d, means this one, this case, this is origin and source 2 is located at distance d, then your path difference will become as a d cos phi, and with the help of these two you have to measure the field pattern and the power pattern. Let's see. So at E at the large distance means far field. So E is equals to E naught. E naught means due to the position of that point located at origin. So that is E naught. But when it is at position D, due to which the electric fields are moving like this, and that electric field is identified as E naught e to the power j psi. So e to the power j psi. And what is psi suffix r? It is nothing but dr cos phi. This is same thing. What is r psi? It is dr cos phi. What is dr? Dr is the far field distance, that is 2 pi d by lambda or beta into d. Now, if I will substitute this equation, I need to represent in terms of cosine, because here we have represented in terms of cosine, we have to disseminate it. So what I will do, E is equals to twice E naught cos of psi by 2 which I can write in terms of psi as dr cos phi by 2, and we have E is equals to 1 plus 1 E naught 1 plus e to the power j psi. So if you disseminate this, we will get twice of E naught e to the power j psi by 2 cos psi by 2. Now if this is maximum value is 1, neglect this component, your value will become the cos of psi by 2. So that means what is the difference? The difference is if you change the position of this one minute. If you change this position of this source 1 to 0.0, this another term is removed and we are getting only in terms of cos of psi by 2. So this is cos of psi by 2. So this is normalized condition, this is 1, and we will have the field pattern as cos of psi by 2. So what is psi? It is dr cos phi. So dr cos phi substitute there. So you will get in terms of cos of that much. That is the field pattern. Due to the change of position, here we are not changing the amplitude, here we are not changing the phase. Both are same. So only the thing is what? The position change. If the position change, amplitude and phase, if it is remain constant, then we are getting the field pattern as cos phi. So once this cos psi by 2 is known, that is the electric field pattern, you can easily determine the power pattern. Only you need to square this cos square term. Cos square psi by 2, that will become as a power pattern. Okay. So this is the case in which same amplitude and phase is available. Next we will discuss same amplitude but out of phase. Okay. So this is the last point which we are going to discuss, and then we'll wind up. And next class we will discuss the different type of antennas, short dipole antenna, Hertzian dipole antenna, what are the radiation intensity, fields and all. Okay, field patterns, power patterns and all those things. So let me discuss the last point, that is called same amplitude but opposite in phase. Same amplitude with same phase we have seen. If we change the position, what will happen? If it is same as it is, what will happen? But now, if the phase is changed, the amplitude is also going to change. So, same amplitude but opposite in phase, how we are going to analyze? So, at a large distance, E is equals to E naught e to the power j psi by 2 minus e to the power minus j psi by 2. So, this is the difference. In same phase and same amplitude, here it is plus due to the 2-point source, but now if it is out of phase, that means it will be one is positive, one is negative, as I have told for dipole. So this is the quite simple example of a short dipole antenna in which one point will be positive, one point will be negative. So one is in phase, one is out of phase. So it is out of phase. So one is in phase is E naught e to the power j psi by 2, and out of phase is minus E naught e to the power minus j psi by 2. Now if it is represented like that, you can disseminate in terms of sign. If it is plus, we have disseminated in terms of cosine, but now it is in minus, we have to disseminate in terms of sine term. So if you divide 2 and multiply 2 and take E naught common, you will get in terms of sine, only we have to multiply j component. So it is 2j E naught psi by 2. If you combine all these things, we will get 2j E naught psi by 2. Now what is psi? Psi is dr cos phi. So that is called path difference. So dr cos phi. So what is dr? It is 2 pi d by lambda. Okay. So this is the same thing what we have discussed in the previous one, but here it is in terms of sine. Always remember that if it is same phase and same amplitude, answer will be in terms of cos. Now if it is in same amplitude and phase is difference, you have to represent in terms of sine. That is the simple difference. Okay. So 2j E naught sine dr by 2 cos phi. Now we will substitute few values to determine which is the maximum value, which is the null value, and where positions can be identified. So for normalized case, 2 E naught let it be 1, d is equals to lambda by 2. So here if you put lambda by 2, you will get dr as pi. So psi is equals to pi cos phi. So that you substitute, you will get E is equals to sine pi by 2 cos phi. Now from where did this pi by 2 cos phi comes? Here dr is equals to 2 pi by lambda, d is equals to lambda by 2, lambda lambda cancelled, so dr is equals to pi. So it is pi cos phi, now divided by 2, so it is pi by 2 cos phi. Now in which particular direction we will get the maximum field, so that we have to identify. So when it will have a maximum field, when your cos term will have the maximum component, and when it will have the 0 component, when it will have as a pi by 2 component. So here pi by 2 cos phi, since it is sine, you have to represent in terms of pi by 2. So it will identify the maximum value. Limit and maximum, how we are identifying like that. When it will minimum, when it is equated to pi terms. Okay. So it is pi by 2 cos phi plus minus 2k plus 1 pi by 2. Now for k is equals to 0, 1, 2, 3, you can put the iteration and identify the range. If k is equals to 0, phi m is equals to plus minus 1. If k is equals to 0 means this is 0. So total value is pi by 2, and here cos phi term will become as plus minus 1. So pi by 2 will be cancelled out. So cos phi is plus minus 1. And when it will have a plus 1 and minus 1, if phi is 0 degree, cos of 0 is plus 1. If phi is 180 degree, cos of 180 degree is minus 1. So phi m is 0 and 180 degree, at which we will have the maximum field component. So maximum field is available only in the direction of 0 and 180 degree. Over. Then in which particular direction the null component is available? Now when the sine terms will become null? When sine term represented in terms of pi. So pi by 2 cos phi naught is equals to k pi. Done. When k is equals to 0, cos phi is equals to 1. When phi is equals to 0 degree, then only the value will become as a 90 degree. So that means when it will have a null value, when the phi m value will become as a 90 degree. When it will have a maximum value, because it is cosine, so 0 and 180 degree. When it will have a minimum value at 90 degree. Okay. Now if it is a half power direction, half power direction means, as we have represented 2k plus 1 pi by 2, make it half. So it is a half power direction. Half power direction means 2k plus 1 lambda pi by 4. So you have to divide this whole component by 2, so that you will get your half power direction. So it is pi by 2 cos phi, it is equals to plus minus 2k plus 1 pi by 4. Now when we will get these values? Substitute k is equals to 0. If k equals to 0 plus minus pi by 4, here it is pi by 2, you will get again in terms of half. So here it is k equals to 0 means 1 we will get at 60 degree and 1 we will get at 120 degree. So these are the special cases through which we can understand the variation of electric field, variation of power pattern. So here we have represented in terms of sine. If it is same phase and same amplitude, we have represented in terms of cosine. Cos of pi by 2 cos phi. But now it is in terms of same amplitude but out of phase, we have represented this one sine of pi by 2 cos phi. And according to phi terms, we are achieving the maximum value and minimum value and half power. So what is the maximum direction? In which particular direction maximum field strength will be available? When the phi m is equals to 0 degree and 180 degree. Why? Because this phi m depends upon cos term. Cos maximum value is plus minus 1. So when it is plus, when the phi m is 0, when it is minus 1, when the phi m is 180 degree. Okay. Now this same thing, how we can justify for the null direction. Null direction means where the field component is not available. So when the field component is not available, when the sine component is equivalent to the pi terms. So the sine of this whole is pi, then sine pi is 0. So pi by 2 cos phi 0 is equals to k pi. So when k is equals to 0, your cos phi will become as a 90 degree. Yes, because if this is 0, something is divided by 0 is always 0 when cos phi is 0, when phi is 90 degree. So this is the null direction where the field intensity is not available. Okay, the field intensity is available in the maximum direction, that is one is 0 degree, one is 180 degree. And half power when it is available, if you divide this component by half, then you will get your half power base. So that I have done pi by 2 cos phi plus minus 2k plus 1 pi by 4. So when k is equals to 0, so it is pi by 2 and this cos phi is equals to 2. So when it is 2, so either it is 60 degree, half means this cos phi is equals to, if it is 1, then it is pi by 4 divided by pi by 2 is 1. So when phi is half, means here I will put cos inverse of half. Either it is 60 degree or it is 120 degree. So this is the half power direction. So like this questions they will ask. In which particular direction the half power is available, in which particular direction null power is available, and in which particular direction maximum power is available for the point source if it is an array condition, and that too having same amplitude with out of phase, same amplitude with in phase. Okay, so these are the basic concepts behind the array point source. So with the help of this analogy, next class we are going to discuss about the various type of antenna. Half wave dipole antenna, quarter wave dipole antenna, then short dipole antenna, and depend upon these variations of dimension, your radiation resistance will change, radiation intensity will change, patterns is also going to change, electric field pattern and power pattern both are going to change, and that all those things we are going to identify, and then we will discuss few numericals on those particular antenna. Okay, so that is the last part of your module 4. So next class we will go through all those derivations, and we will wind up in this particular week only for module 4. Next week we will discuss briefly about module 5, which is very easy, only theoretical part is available with small derivations. Okay, so for the time being, thank you all.